Okay, so yeah, if you want to open up your It's Learning, there's a quiz for today's lecture. It's just called Mineral Properties Lecture, Minerals Lecture 2 Quiz. And you can follow along and take it while we go. It's just a one short question little thing.
Mr.
Okay?
Gambling, she noticed the wet dog smell too.
So what?
She noticed the wet dog smell outside too.
I got nothing. I don't know.
That's so weird. It
I
has
don't
to
know.
be some sort of thing to do with the weather.
So the first property we're going to talk about, okay, is a rather unique property that some minerals have. Anybody? Anybody?
Explosion?
Not just any explosion.
Nuclear fission.
So that was 1945 in New Mexico when we dropped the A-bomb to test it out, right? I mean, tremendous amounts of power. What was left over after this impact was actually a whole bunch of melted sand. So the sand in the desert melted, it fused together, and it's radioactive. In fact, the government buried a bunch of it up because they didn't want people getting out there and removing it, but it melted it into green glass. And I just so happened to have been able to procure some of that green glass from this site. This is the Trinity site, and it was affectionately named Trinite. Now, is it technically a mineral because it was man-made? No, but it is glass from this impact, right? So I'm going to show you guys some of this. Now, some minerals are indeed radioactive. Get out my Geiger counter here. So you're going to kind of come around here, you guys can see it a little bit. This is Trinite from New Mexico, from that bomb right there that you're seeing. This is what happened to the floor of the desert when it got impacted. Set that guy in there. And I'll turn on the light so you can see. It's totally fused green glass. Totally fused. Inside. See how melted it is? I've got a Geiger counter. You wouldn't really know unless I put a Geiger counter on there, would you? Make sure this thing's working.
The question is, why do you have that?
So there's some radioactivity being given off of that, right? It's not super hot, but yeah, I mean it's radioactive glass from the impact of the first nuclear bomb that was dropped. Yeah, oh, there's a little bit. Oh yeah, right? Now on this other one, I've got some metaturbinite, which is a heck of a word to say. This is essentially uranite. This is uranium. This is raw uranium. Okay. Is that not beautiful? Like, look at that. It's a beautiful green. Most radioactive minerals are just strikingly gorgeous. They're bright orange. They're bright green. It's one thing I always do when somebody brings something that's like that. I always get out a Geiger counter or something like that. That's just too pretty to be real, right? But this uranite is a little bit hotter. A little bit, right? So there's not enough here to be really dangerous to you, even though that's pretty scary. I've got it on 1x on the counter here. So it is giving off. Watch how much the radioactivity reduces the further I get away. So two things had to do with radioactivity and how dangerous it is. One, of course, is proximity. The closer you are to it, the more you take, right? The other thing is time. So being around radioactive material for long periods of time is much more dangerous. So Madame Curie, who had that pendant hanging around her neck, it might not have been that radioactive, but she had it on herself every day, right? That's why she got cancer and died. So we do mine this stuff for our nuclear reactors and things.
Why does it give people cancer?
Because the radioactivity that comes off of that happens to be, you can think of, there's different types of radioactivity. So some of it is just like gamma radiation, which is wavelengths of light, right? It's just light. It's just very short wavelengths of light. Happens to be the same length or shorter than the DNA in your cells. And so rather than just passing through your cells, it interferes and interacts with the actual parts of your cell, like your DNA. And it can cause your DNA to spontaneously convert into the wrong letter or wrong base, right? And so you can end up with mistakes in your code just like that. And if it screws up the cell cycle where your cells have to replicate, right, and it gets out of control, then they just keep making more and more and more cells and don't stop. So yeah.
Theoretically, you could get mutations from it.
Yes, that's exactly what we're talking about. So this is, it's not super dangerous. I wouldn't show you guys something that's really dangerous. And even just putting it in the metal case stops a lot of the radiation. Right? So I store this actually between some different pieces of metal, so it's a little bit stopped. If I had some lead, it would be better, obviously. But even just the radiation coming off of that, a lot of it stopped just by the little Altoid tin. Right? But I don't hang out with it all day either. So I certainly don't put it under my bed or around my neck and hang out with it. But some minerals are radioactive, and that's where we get this stuff. They mine a lot of radioactive minerals, uranium in the Grand Canyon. So that's why parts of the Grand Canyon are not safe to camp in or even be in, because they've been digging uranium out of the ground there, and it's leached into the water in places. Heard a story a while back ago about a guy who, this is a true story, it was a news article, the ranger station there at the south end of the canyon, there's like a big ranger station, like gift shop sort of area thing if you go to the Grand Canyon. Apparently, they were cleaning out an area and they found a bucket. And it was a bucket that was full of radioactive stuff that somebody had scooped up and just kept in there as like a doorstop. Like I've got buckets that are doorstops out here. And they didn't know, and nobody had tested it, and it was really hot. Like there was a lot of radioactivity in there. And they had to go and deal with that and clean it out. But it was a real kind of scandal because how many people had been in there, hanging out with this stuff, and it was a bucket like this full of radioactive stuff out of a mine, right? You think that they'd know better than that. The next one we're going to look at is called fluorescence, which is an awesome, awesome thing. Now, I don't know if we can pull this off here. We may have to go into the back store closet. I think if we go in sections, we can do it. Pause this. Let's finish up here. Here are the rest of the things we're going to talk about. So mostly we identify minerals into groups based on what their composition is. And if you look at our Earth, almost the entirety of our crust is made up of two elements. Can you see what they are? Oxygen and silicon, which isn't surprising. We breathe this stuff, right? But these are actually very light elements, so that's why they floated to the top of the molten scum that used to be our Earth, right? So oxygen and silicon are the two most common minerals in our crust. You might want to make note of that. Two most common minerals in our crust. And then there's little bits of everything else right here. This is mainly the rock-forming minerals. These are the classes of minerals. There are lots of them. You don't have to remember them all. We'll mention one in particular here in a second, the silicates. Most rocks on our planet, on our crust, are formed from the silicate minerals. And they have a formula of SiO2. So silicon and oxygen. How about that, right? They're made of the stuff that's mostly present on the Earth. The other groups have different things. The oxides have an oxygen, sulfides, sulfur, sulfates, SO4s, halides have chlorine or fluorite. They've got, or fluorine, they've got, these are the salts. We usually think of them as the salts. Carbonates, CaCO3s. They've got calcite, dolomite, might be the minerals in there. Native elements, copper, silver, gold. Those are all actual elements on the periodic table that are minerals. So there's some that are like that. So these are the groups of minerals. If we were to classify them, if you took a class on mineralogy, you'd memorize every one of those formulas. Okay. So everybody can probably answer the question in their paper right now, from that. Here's the two main groups of minerals. We kind of go, is it a silicate or is it a non-silicate? So we say, is it made of the same stuff that the Earth's crust is made up of, or is it made of some other stuff? So silicates have silicon and oxygen. Non-silicates don't. How about that? Okay. An example is pyrite, which is FeS2, iron sulfide, iron and sulfur combined, versus feldspar over there, that pink one, which is a potassium aluminum silicate. But if you look there, you've got silicon and oxygen in there, so that makes it a silicate mineral. Okay. many minerals are silicates. Nearly all of them are, if they're a rock-forming mineral. Okay. So you might be asked to figure that out here in a second. Cool. Everybody can answer that question on their quiz. All right, let's trudge through the silicates here. Like I said, they're the rock-forming minerals. They make up about 95% of the crust volume, and just about over 74% of the mass that's of the crust. So even though they might not be the heaviest thing, there's so many of them, they still make up just about all the crust. So quartz is one of these. Many of the minerals we've looked at are silicates. What makes them special? Well, when they're bonded together, they're actually 4 atoms of oxygen bonded to one silicon atom. And there's a picture down there. It makes this tetrahedral structure where there's like a little pyramid with 3 oxygens on the outside and then 1 little silicon in the middle. So oxygens are bigger. That's why it gets that funky straight shape. The way these things stick together determines what mineral we have. And there's lots of ways they can stick together. Here's some quartz, and you can see like it even kind of resembles the shape of the silicon tetrahedron there. I'm going to kind of cruise through these quick, it's not too important. Gems, another type of mineral, is any mineral that's got special value. So I know you've seen gems before, like diamonds, hardest mineral on the table, right? Tourmaline, it's a special watermelon tourmaline, it's got looks like watermelon. Aquamarine beryl, beryl's a real, can be a very expensive mineral. So yeah, we sell them. The rarer they are, usually minerals that are considered gems are hard because otherwise they fall apart, right? So most of the minerals that you'll see like around necklaces are gems are real hard. To cut them, we use a special tool. It's got this, it's called a lap, and it's got basically this belt on it that's made up of ground up diamonds. So the diamond dust is what we use to basically cut and polish most of these really hard gemstones. And so this thing's got an angle on it so it can cut these angles. If you've ever seen a diamond, this is the quintessential diamond shape. That's not how they actually form in nature. We make that. So they don't really look like that when they come out of the ground. They're actually kind of ugly looking. But we cut this shape, and the reason we do that is because as light enters this specific geometric pattern, it bounces around in there and reflects in all sorts of different directions and makes them just brilliantly sparkle. So it like comes out in every direction. So when a jeweler's looking closely at a diamond, they're trying to see how faceted it is. Are the facets all correct and in the right placement to make it the light just sparkle when it comes out? That's one of the reasons people really like diamonds. You could do the same thing to a piece of quartz, and it would probably look pretty close, right? And we do that. Here's a diamond pit mine in South Africa. Terrible working conditions. Hundreds of degrees down at the bottom of that thing. Like so hot, some places you can't even touch the walls because they're so deep. It's hot down there. There's a diamond in the rough. That's a real diamond that came out of a diamond mine. Not nearly as exciting. How would you know it's a diamond? Well, nothing else would scratch it. You couldn't scratch that with quartz. You could easily scratch the surface of a plate, right? The only thing you're going to cut that with is more diamond. So they're formed way deep where there's tremendous pressure down there. And yeah, they're made out of carbon. Rocks are made up of minerals for the most part. And this is the rock granite. You can see the quartz in there is a little clearish grayish spots. The potassium feldspar is that pinkish looking color in there. The micas are the little black chunks. They'd flake out. You guys already learned biotite. So we'll learn these rocks somewhat based on the minerals that are in them. And I'm going to list these for you because you're going to see these in a minute when we go in to do our lab. Quartz, orthoclase feldspar, microcline, which is another potassium feldspar, elbite, which is a plagioclase feldspar. We're going to group them into 2 broad groups, the K spars and the plage spars. Biotite mica, we learned that one already. Olivine, which is a green mineral, and hornblende, which is kind of a junky looking blackish mineral. Okay, so we'll learn those. There's also some minerals that don't form a lot of rocks, but are really common in Indiana. And we'll learn those. We have gypsum, which we mine here for wallboard. Pyrite, fool's gold, can be found here. I find it actually pretty often in gravel, like outside my house. Sphalerite's kind of a weirdish black one. It's down here on the right. Can you guys tell what this one is here? Pyrite. Can anybody tell what this one is? It's black. It's very heavy. Yep, it's close. Galena. Yep. So it's a piece of sphalerite connected to two other minerals. And then of course calcite, right? Most of our minerals in Indiana are found here. Almost all of them are found inside geodes. This is chalcedony, that's that bubbly form of quartz that's inside of a geode. Here's some of the ones we're going to try to identify here in lab. These ones right here are known as the rock-forming minerals. These ones right here are just some of the ones that are super common in Indiana that you'll see just walking around. So you might find some of these for your collection. Probably not gypsum way up here, but calcite and pyrite are totally fair game. Okay. These are metamorphic minerals, so these help us figure out how much a rock has been squished and cooked. So some of these are kind of special, like garnets can be a gemstone. So we'll see how to find those here in a second. But being able to identify a couple of these minerals can help you figure out how squished and cooked the rock was when the mountain formed. Okay, like what degree of metamorphism it experienced. They kind of tell us a little bit. Okay, we'll stop that there.